There we go. Okay. I think we're all set. Sorry. Um, okay. So, section 4.6. I've done a little introduction to cryptography, and we're going to jump into RSA per se today. Yeah. Okay. So RSA stands for Rivest, Shamir, Adelman, who are the inventors or discoverers of this protocol. This goes back to 1976. Um, this said, the same protocol was actually discovered 3 years before by Clifford Cox in Great Britain, but he was working for the British government, so he couldn't publish his results. So it was declassified many years later, 97, but the name has stuck. So it's RSA. So Clifford, well, shouldn't have worked as a secret agent, I guess. Tough luck. Okay, so the protocol is based on number theory. That's what we've been building up to in chapter 4. So here is the structure, the overall structure of RSA. So again, remember we have Alice and Bob and Eve, right? So Alice wants to send something to Bob, and Eve is intercepting whatever Alice is sending, and hopefully Eve doesn't figure out what it means. Okay. So Bob wants to receive a message from Alice and possibly many others. And Bob is going to create an encryption key which is public. That means that anybody can see the key to encrypt. And that includes Eve. Eve will have the public encryption key. Okay. However, Bob has a decryption key. So these two things are different. The encryption key and the decryption key are different, obviously. And that's the whole trick. So how do you do this? How do you create different keys? Okay, so here is the actual ingredients. So there's a couple of things I should say. So the first thing is the way I'm going to present this makes it sound as if we use RSA to actually encrypt all communications, but that is not true. It's not efficient enough. So what RSA is actually used to is to exchange an actual symmetric key for a completely different protocol. Okay. But as we talked about yesterday, we need to exchange this key in a secure way, and that's the way to do it. So you use a public key encryption protocol to send a key, an actual symmetric key of a standard cryptography protocol. Okay. But here it makes it appear as if we're actually sending messages. So we're going to use letters, but so it could be anything. It could be bits, whatever. But here it's letters. Okay. Um, so Bob is going to pick out two prime numbers, P and Q, which are very, very big. Okay. So let's say 200 digits for each of these primes. And these are to be kept secret. This is really important. If these primes go out there, then we're screwed. Okay, so this thing just fails. Okay. Um, you can find large primes efficiently, so that's not a problem here. Okay, so, and now Bob creates an encryption key, and this is public, so everybody can see this. Okay, so it's a pair of numbers, N and E. N is the product of those two big primes, right? So remember the basic idea is that it's hard to factor, right? So if someone sees N, if P and Q have 200 digits each, then N has about 400 digits. So this thing, you have to factor this number into two primes. Everybody sees it, knows it's the product of two primes, If you can factor, then you've got it. You can break the code. If you can't factor, it seems unlikely that you can, but that's another story. Okay. So n is the product of p and q, and e is an integer that Bob has computed in advance with the property that it is relatively prime to p minus 1 times q minus 1. So that might look weird right now, okay? But you will see very soon that it'll make perfect sense, okay, why we want this, okay? So n and e are public. Everybody can see n and e, okay? Bob is going to compute an inverse of E mod P minus 1 Q minus 1. We know this exists, right? Because E and P minus 1 times Q minus 1 are relatively prime. We know E has an inverse mod P minus 1 times Q minus 1. Okay, we call it D. So remember that we can actually compute this efficiently by using the Euclidean algorithm and backtracking. So I didn't show you all the details on what it means for this to be efficient and fast and what's the, we're not going to go there. We don't have time. Okay, so you'll have to believe that this is efficient. If you don't believe me, then you'll go ahead and have to read about it by yourselves. Okay. I hope I'll have time at some point, maybe to do a little lecture on all this thing that I've been shoving under the carpet, but even then, so we'll see. Okay, so Bob has an inverse of E, mod P minus 1 Q minus 1, and Bob keeps this secret, this, so ND. So notice that to compute D, it seems that you have to know what P and Q are. From P times Q, how can you figure out what P minus 1 times Q minus 1 is? I mean, it's still a question that maybe it's possible with all this public information, maybe it's possible to find out what D is, or AD, but let's just not go there, because this like really technical and cutting edge and very, very tricky. So let's just see that intuitively, if you don't know what P and Q are, figuring out what P minus Q times Q minus 1 is, it doesn't appear to be obvious or easy. It is not obvious, that's for sure. Okay. All right. So again, what are our RSA keys? So we have our two primes, P and Q, which are different. N is equal to P times Q. The encryption key, this is public, is the pair NE. N is the product of the two primes, and E is some number that is relatively prime to P minus 1 times Q minus 1. The decryption key is the pair ND. D is an inverse of E, mod P minus 1 times Q minus 1. Okay, so that's, everything is there. So how does this work? Somehow this slide, this is very, very paradoxical. This slide is actually totally uninteresting from a technical or theoretical point of view. Is just, it's like really silly, but somehow everybody has trouble with this on the first reading, and that includes me. So it just looks weird, but it's like super simple. Believe me, this is really not hard. Okay, so the messages we're going to encode are written with letters A to Z. This is just for the purposes of this example, okay? That's, so now we're going to be writing words with these letters, and you see that we're using 0, 0, 0, 1, 0, 2 for the first letter, so that every letter has exactly 2 digits, okay? So now I want the blocks that I'm going to encode, I want them to be numbers, which will be these numbers for these letters stuck one after another, okay? What I want is for this to be, these numbers to be less than n. Okay, this is really important. Okay, so the question is, what's the biggest word that I can write, right, so that its number will be less than P times Q, this little n? Well, the biggest pair that I can use for a letter is 25. Okay, so you stack up 25s next to one another, like Z, 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 Z. Okay, that's the biggest number you can create with letters. Okay, and you stack them up as many as you can, but still staying less or equal to n as a number. Okay, so that's what this big N means. Okay, so it's multiplied by 2 because we're using 2 digits for each letter. Okay, so here's an example. If P and Q are 43 and 59, which would not be good if you're actually using this in the real world. They're a bit small. Okay, so little n is P times Q. It's 2537. Okay, so now I want to stack up as many 25s next to one another, but still getting a number less or equal to 2537. Clearly, this is 2525. If I stack another 25 there, it's too big. That number is too big. Okay, so 2525 is the biggest number that I can write of this form, which is less or equal to 2537. So this will be the length of my blocks. It'll be 4. Blocks will be length 4 for this choice of P and Q. Okay, so sorry.
Is 2n the length of that?
Yes.
Oh, okay.
Yes. The 2 multiplied, the big N is the number of letters, and 2 multiplies because each letter requires 2 digits. So yes, 2n is the length of the blocks. As in this here. Yeah, I know this is confusing. I mean, it's just weirdly confusing, but actually it's very simple. I don't know. It's okay. So again, think of how many, so what's the, if I have to send a message, I write it down as a number, and I want the blocks to be no more than little n. Okay, so I really want my blocks to be numbers which are less than P times Q. And this is crucial when we're going to encode and decode. Okay, so I want to take these blocks as big as possible. So I stack up as many 25s as I can, still having a number less than P times Q. Okay. All right. So yeah, so here's an example. So the message boat. So there are 4 letters. Okay. So that means that if you cut it up in blocks of size 4, you got B here, 0, 1, O is 14, A is 0, 0, and T is 19. Okay. So this would be the message we want to send. Okay. Okay. But in blocks, we're going to send blocks separately. Okay, so what's the encoding? It's very simple. Okay, so if M is your, yep, Jacob? Nope, you raised your hand, maybe not.
Can't hear you, Jacob.
I can't, if you're speaking, I cannot hear you. Your mic is on, but Jacob? Yes? No? Okay, so that's an accidental raised
He
hand.
wrote in chat.
Oh. Oh, okay, I see, I see.
Okay, it should be fixed now, maybe?
We can hear you. Yeah.
Yay, thank you. Sorry. Could you go back to the previous slide?
Yes. There you go.
I'm wondering if at the bottom, if n was equal to something like 25, 24, would we be able to write it as blocks of 4, or
No,
would it be less than that?
Good point. So if little n is 25, 24, then the block would be of length 2.
Okay.
20, yeah, absolutely.
So we can only put 25s.
Exactly.
Okay,
Exactly.
perfect.
Yes.
Thank you.
Yeah. Okay. So, all right. Yeah. So how's the encoding go? M is your block. It's a number, right? Which is less or equal to little m. Okay. And how do you encode it? You raise it to the exponent E, which is the number we chose, which is whose GCD with P times 1 times Q minus 1 is 1, right? So we raise M to the power E and we reduce mod N, okay? Now this has to be done efficiently also. I mean, we have to be able to compute this properly. So it's exponentiation, it can be done. I will show you at the end of these slides how this is done, okay? So there is a fast way of computing exponentiation while reducing, okay, mod N. So this can be done. Okay, so C will be the encrypted block. Okay, so if you have a long message, you chop it up in blocks and you encode each block. It's a number, raise it to the power E, reduce mod N, send that. Okay, so that's it. So here's an example with the same primes. So P is 43, Q is 59. So our little n is 2537. So we computed, so we can put 2525, but not another one. So our blocks have length 4. And Bob decides to choose E equals to 13. So what is the key? Yeah. So what is the important thing is that if you take P minus 1 times Q minus 1, which happens to be 42 times 58, the GCD of this E should be 1. With this number here, we're good. Okay. So the public key is 253713. Let's say that Alice wants to send the message stop. So blocks have length 4, so that's 2 letters for each block. So if you look up S and T, it's 18 and 19, and O and P is 14 and 15. So these are our 2 blocks. So these are the numbers 18, 19, and 14, 15. And then we raise them to the power 13, reduce mod 2537. So you see the number, even for small primes. So think if those primes have 200 digits each, and the E is pretty big, you can see that, I mean, you need to be careful how you're computing this, right? So numbers will be very big, okay? So we raise 1819 to the power 13, reduce mod 2537, we get 2081, okay? Do the same for the second block, you will get 2182. Okay, so the ciphertext that is sent is all those blocks together. That'll be 2081, 2182. That's what will be sent out on an open channel. Okay. Now again, Eve has the public key. Now she will see this ciphertext question. Can she figure out what the original numbers were, knowing only these things? Okay, that's a good question. Okay, all right. How do we decrypt? That's the big point, right? That's where the protein is. So Bob will receive C, which Bob knows is big M to the power E reduced mod N. Okay, what is E? It is an inverse of D. So they're inverses mod P minus 1 times Q minus 1. Okay, so how does Bob get M back from M power E mod N? Okay, well, it's actually pretty easy. I mean, it's easy to tell you what Bob needs to do. Okay, but what's not so obvious is why it works. Okay, so again, C is M power E mod N. This is what Bob receives. Okay, we have E times D is congruent to 1 mod P minus 1 times Q minus 1. I'm going to translate that. We know it means that E times D is equal to 1 plus some multiple of P minus 1 times Q minus 1. Okay, so now Bob will raise C to the power D. So here's what happens. Okay, this will be, so C is congruent to M power E. So if you raise both to the power D, they're congruent mod N, obviously. So we get M to the power E to the power D, which is m to the power e times d, which is m to the power 1 plus something times p minus 1 times q minus 1, all this up to congruence mod n, okay? So what are we going to do with this exponent? You can maybe guess exponent p minus 1, you're thinking Fermat's little theorem might play a role here. Okay, so let's take a look at what happens. Okay, now I put this in I should change this slide because it looks like it's like super important. It's not. Okay, this is not important. I'm just making this little technical hypothesis because the argument is different in the case where P and Q do not divide big M. Okay, you can be really unlucky. You write down a message that you want to send. Okay, so I'm Alice. Okay, I want to send my message. I don't know what P and Q are. Okay, it's irrelevant anyway for me. I just need to know what P times Q is. So I write down my message. Maybe by some incredible bad luck or luck, I don't know, P or Q or both actually divide my message, the number of it could happen, okay? So the decryption method will still work, okay? So but the argument is different. So I'm just putting this hypothesis here just to make you aware that the argument is different. Okay, I'll get back to this. It's not a big deal. It's not really important. Okay, so I'm making the hypothesis that we weren't very unlucky, and neither P nor Q divides the message M. Okay. Okay. First observation, which is something I should have mentioned earlier, but it's sort of obvious, is that if two numbers are congruent mod n, then they will be congruent mod any divisor of n. Why is that? Well, if n divides b minus a and p divides n, then p will divide b minus a, okay? So if a, in my case here, n is equal to p times q. So if a and b are congruent mod n, they will be congruent mod p and mod q. It's okay. So let's just now see what we've got. C to the power d. So Bob again receives C, raises it to the power d. Okay, what are we getting? We're getting m to the power 1 plus k times p minus 1 q minus 1. This is equivalent mod n, and in particular mod p. Okay, so this is true mod p. And let's just rewrite the right-hand side. You see that this is m times m to the p minus 1, all this to the power k times q minus 1, which is actually irrelevant because Fermat's little theorem tells me that m to the p minus 1 is 1. So that just goes away. It disappears. Okay? So c to the power d is congruent to the original message mod p. Okay? By this, the whole thing is symmetric. So if you just do exactly the same computation, but using q instead of p, you will find that c to the power d is congruent to big M mod q. I understand that I'm going through this, and if you've never seen this before, which is probably the case, that it's not so obvious what I'm doing, okay? But if you spend some time reading this with paper and pencil, it's not hard, okay? It's just using what we did in chapter 4, okay? So Fermat's little theorem tells you that if you take the encoded message C, you raise it to the power D, this number will be congruent to the original message mod P and mod Q, okay? So this is an application of Fermat's little theorem, okay? So let's go to the next slide, okay? So now I've got that. C to the power D is congruent to M mod P, and it's congruent to M mod Q, all right? But what does the Chinese remainder theorem say? It says that there is exactly one integer between 1 and little n that has this property, okay? And so that has to be m. Remember the way we chose our blocks, the numbers are less than n, okay? That was the point, okay? So between 0 and n minus 1, there is exactly one number that is congruent to m mod p and m mod q. That's m. That's the only one, okay? So c to the power d is congruent to big M mod n. So if I reduce c to the power d mod n, I get exactly m. I've decoded the encrypted message. Okay? Yes. I swear this is not so bad. If you're not quite with me here, I'm saying it's really not so bad. Don't panic. Don't be scared. Okay. So, okay. So that's the proof that RSA works, except if you were really unlucky and you wrote down a message. If you're Alice, you're sending a message and P or Q or both happen to divide your message. But in fact, it still works. It's just the argument is different. Okay. So let me just add that for completeness sake. I've got let's go here. Okay. So I don't want to go through this slide in detail. I just don't. Okay. I don't want to mix you up. Okay. But it's there. So if P or Q happens to divide the message M, it still works. If you take C to the power D, you will get back M. And it's the Chinese remainder theorem. Is just that you can't use Fermat's little theorem. You're not allowed because P divides the base of your when you're taking your exponent. Okay, so you're not allowed, but it still works. Okay, it's an exercise in the textbook, and it's an easy exercise. Okay, so it's there. So let's not go into detail. Just keep in mind that C, when you raise the encrypted number to the power D, you will always get back what you want. It's just that the argument to prove this is a little different in this case. That's all. Okay. So I'm going to go back to my little example here of decryption. Okay. So same primes, 43 and 59. N is 2537. Length of blocks is 4. And we had E equals to 13. Okay. So you can easily compute. You could do this by hand, right? This is doable by hand, no problem. It's quick. You can find D equals 937. So what is D? It's an inverse of E mod P minus 1 times Q minus 1. Okay. So now we receive the ciphertext. This is what we receive: 09810461. Blocks have length 4. So I'm going to decode each block separately. What do? I raise those blocks to the power D reduce mod 2537. So the first one is 0981. Raise that to the power 937. That's my D. Reduce mod 2537, I will get 07004. Okay. Do the same for the other one. You will get 1115. And you know this was the original message M in both, I mean, M1, M2 if you want. So you just look up what these numbers mean in terms of letters. And in this case, it's help, H-E-L-P. Okay. Which is not relevant to this whole thing. It doesn't matter. Okay. So there's no real mystery behind this whole thing. Okay, it's just to encode, you raise to the power E; to decode, you raise to the power D. These powers will cancel out because of Fermat's little theorem and the Chinese remainder theorem combined. Okay, so that's essentially the whole story, the whole idea. Okay. All right. Now, any questions up to this point.
If P and Q are secret, how will the receiver of the message decrypt if we need P minus 1 and Q
So
minus
the receiver of the message knows P and Q. That's the bank. Okay. So Bob knows P and Q.
All right.
It's Alice who's sending that doesn't know P and Q. That's only the senders do not know what P. Yeah, to decode you need P and Q.
Okay.
Well, okay. Again, to be very, very precise, you might not need P and Q. You can, in the book, there's a discussion of this not in much. I'm not sure if it's in the book, actually. I'm sure maybe I read this somewhere else. I don't know. But if what you need is an inverse of E mod P minus 1, Q minus 1, that's all you need to decode. You don't, I mean, it seems like you need P and Q. Nobody's proved that. It's not known yet that you actually need those. I don't know what the status of this is. But there's no big public breakthrough, that's for sure. Okay. Okay, let me show you exponentiation. This you will need. You will need this because even your calculator is not going to be able to do all the problems you want to do. Okay. So we want to be able to compute exponents, right? Either to encode or decode, we have to compute like big powers and reduce mod n, okay? If you look in section 4.2, there is an algorithm. The algorithm I'm going to show you is there, okay? But the basic idea is very simple. I'm just going to go through an example and you'll see how this works, okay? So the trick is successive squaring and reducing as many times as you can, okay? So I'm going to show you with an example, which is 3 to the power 644 mod 645. Okay, so yeah, I wrote this. It looks like you can use Fermat, but you can't because 645 is not prime. So there's no reason why this should be congruent to 1. Okay. So how do we do this? Well, the trick is this. Okay. So I'm going to write 644 in binary, and it turns out that it is in binary. It's 1010000100. Okay. Which means what? It means that 644 is 2 power 9 plus 2 power 7 plus 2 power 2, right? Writing a number in binary means writing this number as a sum of powers of 2, okay? So if you rewrite 644 as a sum of powers of 2, then 3 to that power can be written as 3 to the power 2 power 9 plus 2 power 7 plus 2 power 2, which can be split up as a product, right? So it's 3 to the power 2 power 9 times 3 to the power 2 power 7 times 3 to the power 2 power 2. Okay. Now, what is 3 to the power 2 power 9? It is 3 squared, all this squared, all this squared, it's a repeated squaring operation. Okay, that's exactly what this is, right? Because if you've got 3 to the power 2 power k, and you want the next to 3 to the power 2 to the power k plus 1, it is, as you can see, it is 3 to the power 2 power k, all this squared, right? Properties of the exponents. Okay, so to get to these 3 powers of 3 and the exponent is a power of 2, you do repeated squaring. Okay, so I'm going to show you what you get. I mean, you can do this by hand, but it's a bit painful. With a calculator, it'll be much easier, right? So I need up to power 2 power 9. So I'm going to look at successive squares of 3. So 3 squared is 9, and I'm reducing mod 645 as soon as possible, okay? Then I square this, so 9 squared is 81. Then I square this, 81 squared. Now I'll reduce 640 by mod 645, you'll get 111. Square that, reduce, you get 66. Square that, reduce, you get 46. Square that, reduce, 126. And you just keep on going. By the way, notice that once you've reached this guy, you know that you're going to loop. So you don't really need to do any computation, different computation from this point. You see it actually loops from this point on, which is interesting. But in any case, we've got all the successive squares of 3 up to this biggest one that we require. Okay, we've got all of them mod 645. And again, this doesn't take very long, right? I've got another slide where I'm going to talk about actually doing this I mean, if you're on a desert island with a calculator, how do you actually do this? Because I've been asked this, not about the desert island part, but how do I do this with a calculator? I'm going to discuss the actual reduction in just a sec. Okay, but let's just finish this computation here. Okay, so 3 to the power 644 mod 645. This is, as we observe, 3 to the power 2 power 9 times 3 to the power 2 power 7 times 3 to the power 2 power 2. These were pre-computed mod 645 by successive squaring. So these were 111, 396, and 81. Multiply those, reduce mod 645, and you get 36. Okay. So all you need to do is square, reduce. That's basically the only operations. I mean, there's some multiplication there, but square, reduce, basically that's it. Okay. So it's not going to take you, you never get really big numbers like that. Okay. Yeah, just in case, how do you reduce mod n if you have a calculator and the numbers are pretty big? So I just put this example, which is part of the previous slide, where I had 3 numbers to multiply. Sorry. So 111 times 396 mod 645. Okay, so I'll have to multiply 111 by 396. Neither of them is bigger than 645, so I can't. I mean, if you're thinking about this, you say, oh, the numbers are not too big, maybe I can factor them, multiply. Yes, there's you can mess around with this a little bit, but otherwise you just multiply them, you get this number. I'd like to reduce this mod 645. How do you actually do it? You do the division algorithm. How do you do it with a calculator? Divide. Okay. You're going to get 68 point some decimals. Okay. And then what you do is you just keep the remainder and multiply by 645. That's basically what you're looking for. Okay. So you remove the integer part. That's the 68, right? You remove that, you're going to get 0.14, blah, 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 blah. Multiply by 645, you get 96. That's your remainder. That's what you want. Okay. You can think about it, but so if you're doing problems and you're doing with a calculator, that's exactly what you're doing when you're reducing mod 645. Okay. I think that's my last slide. Yes. Okay, so RSA, you've got the full description and why it works, okay, and how it works. I've added how to do exponentiation by hand calculator and how to reduce mod n. So you've got all these things at your disposal. The WebWorks, I'm sorry, it's I'm getting there. It will be there tomorrow for sure. Okay. And you'll be asked to do some simulating RSA, right? In theory, you should be doing this by calculator by hand, and I recommend doing it because you can see you always have to get your hands dirty. That's how you see how things work. Okay. All right. Any questions, comments?
Could you go back to the first slide where you did the decryption? Or the... Or could you go back?
This one?
Yeah.
Oops. This one.
Yeah, this one.
All right.
What is that? What are you saying at the top? I didn't quite...
Okay. So if A and B are congruent mod n,
Mhm.
and n is P times Q,
Right.
okay, then I claim that A and B are congruent mod P and mod Q.
Okay.
So if you're congruent mod 6, then you are congruent mod 2 and mod 3 also, because 6 divides the difference, and so 2 and 3 also divide the difference. So the numbers must be congruent mod 2 and mod 3 also. Right? The two numbers are congruent mod n means n divides the difference. And if P divides n, I should have written that here, right? P divides, yeah, I should add that to this slide. So P divides n, which divides B minus A, so P divides B minus A. You see it? Okay, wait. Let's do that. Okay, so I've got A congruent to B mod n.
Mhm.
N is equal to P times Q.
Yeah.
Okay, so what this means by definition that n divides the difference, right? So two numbers are congruent mod n if n divides their difference. Agreed?
Yeah.
All right. Now, n is equal to P times Q. So P divides n? Yes. Please say yes.
And Q. And yeah, and Q divides
You-
n, yeah.
Okay, yeah, all right. Okay, so P divides n divides B minus A, so P divides B minus A.
Oh, that's one of the properties we saw earlier?
Yeah, so, and so by definition, this means that A is congruent to B mod P also. Same for Q. Right?
Okay.
This it's if there's something confusing you here, I mean, if you spend like a minute on it by yourself without all these people staring at you, so you'll see, you'll go, oh yeah, it's just no problem.
Right.
All right. I don't know how to. Would an example help? I don't know if A is congruent to B mod 15. Okay, so this means that 15 divides A minus B. So A minus B is a multiple of 15, so it's also a multiple of 3, and it's also a multiple of 5, for sure. Right?
Okay.
So by definition, A is congruent to B mod 3.
Mod 5.
Yeah, and mod 5. Oops.
Okay, thanks.
So the bigger the number, the finer the congruence, right? It tells you more about how A and B are. If they're congruent mod 15, you get more information than if you only know if they're congruent mod. Of course, Chinese remainder theorem tells you in a sense that you can go back. But that's another story. All right. Other questions?